Hi everyone, my name is Violet Torrey and I am a software developer and researcher here at the Software Engineering Institute in the Artificial Intelligence Division. Today I'm going to be presenting work titled Moving Explainable Artificial Intelligence from Research into Practice, Defining and Validating an XAI Process Framework. Through this project, we're working to address gaps between explainable AI, research, and practice so that explainability can be introduced to more real-world mission systems. Our project focuses on addressing practical challenges with implementing and maintaining XAI software. Explainable AI, or XAI, is a research area that looks to make model behaviors and outputs more understandable to humans. Explainability can act as a critical tool for enabling digital transformation by making AI systems more transparent, but the current implementation practices for XAI are confusing, time-consuming, and not often performed. Our proposed solution is to produce a process framework that AI practitioner teams can use to select, implement, and employ XAI techniques appropriate for their systems and users. This framework will build on existing requirements engineering and design-focused XAI process frameworks by creating an end-to-end process for defining, building, and maintaining explainability software. Our 2-year MTP project looks to address the growing need for transparency in mission systems by proposing and validating a process that can be used by AI practitioner teams to introduce explainability within their systems. Our project focuses on 3 main activities. 1, a literature survey of existing process frameworks and perspectives on practical XAI implementation. 2, a case study building explanations for AI matching algorithms used by a wildlife nonprofit called WildMe, and 3, a case study with an AI system designed for the mission space. Along the way, we'll be capturing our lessons learned through a process framework that we will share with both the XAI research community and stakeholders from defense and intelligence communities. So to provide more context for our work, I'll give a brief introduction to deep learning models and some of the challenges that deep learning models present. Deep learning models are a category of machine learning model that contains multiple layers of neurons. In domains such as computer vision or natural language processing, deep learning models have enabled powerful new capability. Convolutional neural networks, for example, have far-ranging applications including facial or image recognition, and transformers are another type of deep learning model that help power large language models or LLMs. As new capabilities emerge, we need to exercise caution to make sure we understand their behaviors and are employing these technologies in responsible ways. Unfortunately, while deep learning methods have enabled exciting new capabilities like LLMs, they've also exacerbated uncertainties. Deep learning models are opaque, meaning that the underlying decision process of the model is not visible or understandable to humans. We can test how models perform on various inputs, but we can't really see under the hood. And as a result, humans using AI to support their decision-making processes may have trouble differentiating between correct versus incorrect suggestions made by AI systems and struggle to build appropriate levels of trust. A lack of transparency in deep learning systems is a major issue for the mission space. To quote Deputy Defense Secretary Kathleen Hicks, "Our operators must come to trust the outputs of AI systems. Our commanders must come to trust the legal, ethical, and moral foundations of explainable AI, and the American people must come to trust the values their DoD has integrated into every application." To realize our government stakeholders' goal of integrating XAI within their systems, explainability must become feasible for real-world projects. Explainability also supports the DoD's ethical principles in a variety of ways. The responsible principle focuses on personnel's responsibility to oversee the development, deployment, and use of AI capabilities. The integration of explainability into user-facing tools enables end users to make more informed decisions about when and how AI suggestions should be taken into account. The equitable principle specifies that the department will take steps to minimize unintended bias in AI capability. Explainability can help detect bias by revealing which characteristics of inputs are most important in reaching outputs. The traceable principle states that capabilities will make use of appropriate, transparent, and auditable methodologies. Explanations can be useful for understanding how and why predictions were made and tracking how these predictions influence our decisions. The reliable principle focuses on having well-defined uses and rigorous testing of AI capabilities throughout their life cycles. Explanations augment testing by introducing other metrics for success that go beyond accuracy. Finally, the governable principle centers around designing and engineering AI capabilities such that detection and avoidance of unintended consequences is possible. Explainability can assist teams in identifying incorrect predictions and unintended patterns of behavior that require governance or intervention. Research into methods for building more transparent AI systems, such as explainable AI techniques, aim to provide users with information they need to reason about model behavior. To generate explanations, typically a simpler and more interpretable surrogate model is trained that provides an approximation of the ML system's decision-making process. These surrogate models can be used to produce explanations that are understandable to humans. Explanations can take many forms, such as heat maps, example-based explanations, or concept-based explanations, depending on the modality, model type, and end-user need. Consider an application where users upload an image of an animal and the application returns the species. The user may have questions about how the application reached its conclusion, especially if this prediction is critical to their work. Heat maps, which are the example on the left, or saliency maps, indicate which pixels in the scene are the most important in the model reaching its output. Saliency maps may be useful to engineers and end users for verifying that the model looks at what they expect. In this example, we expect that the body of the dolphin would be used for classification and not erroneous elements of the image such as the water around the dolphin. Example-based explanations show the end user examples of images from the training data that were important for the model's prediction. These visuals may help the end user reason about the validity of the model's prediction based on how relevant the example images appear. And then on the far right, we have concept-based explanations, which use text-based concepts to indicate why an output was reached. In this example, specific regions of the tail help the model identify that this is a bottlenose dolphin. Subject matter experts may look at this explanation to verify that the same features they would use to classify the image are being accounted for. To ground this work in the state of the art, we conducted a literature survey looking at over 150 resources related to XAI implementation. We then conducted an in-depth analysis of a corpus of 10 process frameworks, investigating both the methods used to develop these processes and commonalities across their content. We found that although XAI research is a popular emerging research area, methods for implementing XAI in practice remain scarce. AI practitioner teams must navigate a web of design needs and technical limitations to produce explanations. Users may have unanswered questions about the system that are obstacles to being able to trust and use the system as designed. These questions can act as a starting point for the process of designing explanations. Designers use this information to select candidate types of explanations and design interfaces for delivering this information. AI engineers then make technical decisions based on the designer's concept to make explanations possible. Translating across these roles and identifying points where translation isn't possible, for example, if the user has questions which cannot be met by current XAI techniques, is a challenge for teams looking to implement explainability. Current process frameworks focus primarily on prototyping rather than producing XAI for production, drawing on standard requirements engineering and design processes, but leaving the needs of AI engineers relatively unaddressed. As AI systems and users evolve over time, explanations may need to be modified or redesigned. AI practitioner teams need processes that account for challenges in building and maintaining XAI systems across every step of the pipeline. To address this gap, we're working on a novel process for incorporating explainability into real-world AI systems. Based on our survey and our knowledge of software engineering and machine learning life cycles, we propose a process framework that builds on common existing stages seen in the previous slide by incorporating AI engineering-specific tasks and challenges related to productionization and maintenance of AI system-specific explainability software. This framework will enable roles involved with making decisions about where and how to use AI systems in the mission space, with methods for defining XAI requirements and ensuring that AI practitioners follow a standardized process for implementing XAI. The first 4 stages of the process help AI practitioner teams ensure they're building the right kinds of explanations. In the first stage, AI practitioner teams set goals for the project and ensure they have a mix of team members, such as designers and AI engineers, to support the process of building explanations. In the need-finding stage, designers meet with end users to understand their questions about the system and any other challenges they may have interacting with the AI. Next, teams can begin prototyping and evaluating potential explanations. These two stages require close collaboration between AI engineers and designers, as translating from user questions to explainability techniques can be complicated and may require interdisciplinary knowledge. The final two stages are our primary contributions to the XAI implementation process. Existing methods tend to focus on the prototyping phase, but don't address the tasks involved with deploying and maintaining explanations in the long term. To provide guidance on these two stages, we will need to answer open questions related to XAI use within real-world systems. For example, how should explanations for single instances be effectively scaled up to provide visualizations for bulk uploads? How often will XAI surrogate models need to be retrained? How will this schedule coincide with or differ from the deep learning model training schedule? How often should we evaluate our explanations and build new ones for new user groups? To validate our proposed process and address open questions related to the XAI lifecycle, we're partnering on an IRB-approved case study with wildlife conservation nonprofit WildMe. WildMe uses a variety of algorithms to assist researchers in tracking the behaviors of individual animals. WildMe's matching algorithms allow users to upload an image of an individual animal or group of animals and return ranked predictions about which individuals are in the images. This process can take the place of physical tagging and provides research teams with the information they need to complete their work. Through our case study, we will work through our proposed process by designing, building, and maintaining explanations for WildMe systems. Through this work, we will gain an understanding of how well our process works in practice and further revise and refine our proposed methods. We'll also gain a better sense of where and when XAI should be used, gaps in current XAI techniques, and ways in which other elements of an AI system can be modified to produce more transparent and human-centered interactions. While our case study focuses on a conservation use case, algorithms for classifying input images or identifying individuals are relevant to sponsors working on systems for use in the mission space. For example, a variety of computer vision algorithms have been developed to help track illegal maritime activity, such as illegal fishing, using aerial imagery. Explanations could be useful in helping teams review flagged vessels before addressing issues at the scene. Likewise, if more detailed imagery is available, such as drone footage, matching algorithms could be employed to track individual vessels of interest. Explainability may be leveraged in these contexts to better understand and vet matches. Collaborating with WildMe allows us to learn and share lessons from open source systems that are used by a wide variety of stakeholders, so these insights can be applied to related systems used in mission contexts. To understand what XAI implementation looks like in practice, we've become embedded in WildMe's AI practitioner team's processes. Gaining an understanding of both user experience and technical decisions made within WildMe systems has helped us learn about the challenges that AI practitioner teams navigate in building and maintaining AI systems. On the UX side, we've attended meetings with WildMe's product designer and customer experience experts to get a better understanding of design decisions within their systems and common behaviors and challenges that end users have. To gain first-hand experience with their systems, our research team has also all made accounts on their systems and explored the matching process for ourselves. On the ML side, we've been sitting in on weekly ML meetings to hear about experiments and projects that the WildMe team is working on, and trade-offs they're navigating between model attributes such as interpretability, generalizability, size, and latency. WildMe uses an array of algorithms such as MuID and Pi to help end users working on a variety of projects that use different kinds of data. Data can vary by species, viewpoint, volume, and location, among other factors. We started the case study in August and are currently in stage 2 of our process framework, or the need-finding stage. Although we're early in this process, we're already learning a lot about XAI in practice. At the start of this collaboration, we thought we would meet with a variety of stakeholders and then jump right into prototyping and evaluating XAI solutions. However, in practice, there's a lot of nuance to the relationships that different end users have with AI systems and the explainability needs that they have as a result. WildMe is currently in the process of shifting from earlier, simpler models to newer, more sophisticated deep learning models. Although their deep learning models, such as MuID, can outperform their earlier models on a variety of tasks, they've noticed that some end users are reluctant to use the newer models because they've grown accustomed to using interpretable heat maps from earlier models to help make their matches. While it's possible to produce heat maps for deep learning algorithms, they can look different and be harder for humans to interpret. We've realized that once explainability is integrated into a system, it can set a precedent for future interactions and reduce trust in new algorithms that don't enable that same functionality. Inference time can also have a big impact on the user's experience. Larger models may take longer to make inferences and slow down the workflows of end users. The trade-off between inference time and model performance is another tension that teams need to navigate when thinking about how to make their systems human-centered. We've also learned that different stakeholders can interact with systems in significantly different ways. The WildMe system displays a score for each potential match to the user's uploaded image. These scores are largely uncalibrated and can vary based on species, viewpoint, and algorithm, and as a result can be challenging for users to employ as they make a match. At the start of the need-finding phase, we hypothesized that removing these scores and providing users with just a ranked list would make the system more usable and lead to better interactions. Longtime users of WildMe systems, however, often gain a sense of what these scores mean for their specific subject area and use this intuition to make comparisons between scores. As we suggest modifications to the user interface and design explanations, it will be critical to think about which experience levels we're targeting and the ways in which users can come to understand and rely on idiosyncrasies of a system they've used for a long time. Other elements of the user interface design can also pose unexpected challenges for users. For instance, the image shown as a potential match can have a big impact on how accurate the user thinks the match or system may be. Even if Jake is the correct match for the image on the left, because a random picture was selected rather than a close match, the user isn't getting a strong visual cue that these are the same individual. In summary, we're seeing that AI systems are not necessarily ready for explainability, nor is explainability the right solution for all user questions. Adding in a heat map to this example page would not alleviate usability challenges related to the user interface design, score calibration, algorithm type, and inference time that are already obstacles to the user's decision-making process. We've learned that taking stock of these issues and determining a minimum viable plan for updating a system before XAI is introduced is an important step to make sure explanations can be processed effectively by end users. Next steps for the need-finding stage include talking with end users to understand what questions they have about the system and its outputs during the matching process. Based on their questions, as well as insights from the WildMe AI practitioner team about user needs, we will begin prototyping explanations using open-source tools. We're setting up infrastructure for prototyping and plan to document lessons we learn along the way about how to set up an effective, lightweight prototyping environment. Once we have implemented candidate prototypes, we will run a survey with end users to understand the impact of proposed explanations on user understandings of model behaviors and their opinions on the degree to which various explanations can support their decision-making process. We're also gearing up for a second case study that would run from about January to October 2024. We're scheduling 30-minute discussions with individuals working on computer vision systems for the mission space that could benefit from explanations. If you believe your project may be a good fit and want to learn more, please contact us at info@sei.cmu.edu. I want to conclude by thanking our awesome team of engineers, designers, and researchers from both the Software Engineering Institute and the Human-Computer Interaction Institute. Our group is enthusiastic about the challenges of implementing responsible AI principles and identifying DoD-relevant solutions. Please reach out if you have any questions about our work or want to discuss how an explainability process framework could be used within your organization. Thank you.